Welcome back to the deep dive. Our mission today is to take those fundamental building blocks we talked about last time, the score function and the loss function, and add the engine that actually makes them work. So just as a quick reminder for you, we set up the basics of image classification. We had the score function.
Right, that's the linear math equation, the 5xeo EP equals what size,
Yeah.
that turns all those raw pixels into glass scores.
And then we had the loss function, which is basically the part that tells us how badly our current set of weights, our dollars, is performing. It's our metric for error.
Exactly. You pick a random set of weights, and the loss function spits out this huge number telling you your model is, well, terrible. So our goal is to find the perfect dollar that gives us the lowest possible loss. And that search process is the third and final piece, optimization.
Okay, so if the score function is how we predict, and the loss function is the critique of that prediction, then optimization is the engine that drives us from, total failure to actual competence.
And what's really important for you to remember is that this whole conversation we're about to have about optimization, this search for the minimum, it's universal.
It applies to the simplest linear model we've been using.
And it applies to the most complex trillion-parameter neural network. The core idea is the same.
The first thing you really need to wrap your head around is just the sheer scale of the problem we're trying to solve. I mean, we're not minimizing a function you can just draw on a piece of paper.
Not at all. The loss function exists in a space that is defined by every single parameter we need to tune.
And when you say parameters, you're talking about the weights in that big matrix.
Exactly.
Yeah.
Let's take our simple linear classifier for the CIFAR-10 dataset. We had, 10 classes? And each image had 3,073 features.
The pixels plus the bias term.
Right, so you multiply those together, and that weight matrix, dollars, has 30,730 parameters.
30,000 dimensions. It's impossible to visualize, but I guess we can imagine taking a slice through it. What would that tell us about the terrain?
Well, if you cut through that loss space in just 1 or 2 dimensions, you start to see what you're navigating. And for the simple SVM or softmax loss with a linear model, the landscape is actually pretty forgiving.
Forgiving how?
When you average the loss over all your examples, it looks like a smooth, convex, bowl-shaped surface. There are no bumps, no sudden cliffs. It's predictable.
That sounds almost too easy, like walking down a smooth ramp. Is it always like that?
Absolutely not. That smooth bowl is fleeting. The moment we switch from a linear classifier to a real neural network, the second we introduce nonlinearities, that entire landscape changes.
Wait, why? Why does just adding a few nonlinear steps suddenly turn our predictable bowl into a chaotic mountain range?
Because linearity is what guarantees convexity, that property that lets you draw a straight line between 2 points and stay above the surface. The moment you introduce nonlinear functions, that property just breaks. The landscape becomes a complex, bumpy terrain full of valleys, cliffs, and plateaus. We call that a non-convex space.
And that leads us to the analogy for today. For this entire deep dive, you need to think of yourself as a blindfolded hiker trying to get to the bottom of this huge, hilly terrain. The height of the ground is your loss value, and because you're blindfolded, you can only feel the slope right under your feet.
And you have to decide where to step next.
Okay, so if you're blindfolded on a mountain range, your first idea might be to just wander around randomly until you stumble into a valley. Let's talk about why that's a terrible idea in optimization.
The first really naive strategies are all based on randomness, and they fail spectacularly. The amount of computation you need for even a tiny improvement is just immense.
So, strategy number 1.
The simplest. Random search. You literally just generate a weight vector, Wiverty at random, calculate the loss, and then do it again, maybe 10,000 times. You just keep the one that gave you the lowest loss.
That feels like closing your eyes, throwing 1,000 darts at a map, and hoping one lands in the Dead Sea.
It's a terrible method, but it does give us a baseline. So on CIFAR-10, a pure random guess would get you 10% accuracy. Random search actually gets that up to about 15.5%, so it's better than nothing, but barely.
Okay, so if that's too inefficient, the next idea is to be a little smarter. Random local search. Instead of jumping all over the map, you just feel around your current spot.
Right. Take your current dollars, you try a small random nudge, a little delta lord, and you only take the step if the loss goes down.
You're feeling around with your feet.
And it works better. Your accuracy jumps up to 21.4%. But think about the cost. In a 30,000 dimensional space, you might have to check hundreds, maybe thousands of random directions just to find one that goes downhill. It's incredibly wasteful.
It's the definition of inefficient. So what we learn here is that finding the absolute global best set of weights by just guessing it's impossible. We need a better way.
We need a system, a way to start with a random dollar and then iteratively, step by step, make it better. Systematically move downhill.
And this is where we stop wondering. Because we don't have to guess the downhill direction. Mathematics gives us the perfect tool for this, and that tool is the gradient.
The gradient is the central concept. It's basically a generalization of the slope you learned in school, but for functions that have thousands of variables.
Right, so instead of a single number for the slope, the gradient is a vector, a whole list of numbers.
Precisely. And that vector is made up of all the partial derivatives, one for each of our 30,730 dimensions. And here's the magic. That gradient vector always points in the direction of the steepest increase.
So to go down, we just flip it around.
You follow the negative gradient. That is the guaranteed path of steepest descent.
Okay, so we know the direction, but calculating that 30,000 component vector seems like a huge task. The sources mention two ways to do it, a slow way and a fast way.
The slow approximate way is called the numerical gradient. It's based on the definition of a derivative. You calculate the loss at your current dollars, then you nudge just one parameter by a tiny amount, dollars, and calculate the loss again.
And the change in loss divided by that nudge gives you the slope for that one direction.
Exactly. But the inefficiency is just staggering. For our 30,730 parameter example, you have to do 30,731 loss evaluations just to get the direction for one single step. It's completely non-viable for any real model.
Which brings us to the fast way, the analytic gradient. This is where we use calculus. We derive an exact, fast formula for the gradient. No more approximations.
So why would anyone ever use the slow way?
Because doing the calculus for 30,000 partial derivatives by hand is, well, you're going to make a mistake. One tiny sign error in your code and the whole thing breaks.
And that's the punchline. This is where the gradient check comes in. It's the pragmatic solution. We use the slow, reliable numerical gradient as a sanity check for our fast, error-prone analytic gradient.
So you code up the fast one, but before you start your big training run, you compare a few of its outputs to the slow one, if they match.
You know your math is correct.
Yeah.
And you can switch off the slow one and rely on the fast analytic method for the rest of training. It's the ultimate quality control.
Okay, now we have a fast, verified way to find the steepest downhill direction. This lets us build the core optimization loop, vanilla gradient descent.
It is incredibly simple. You just repeatedly evaluate the gradient and then update your parameters by taking a small step in that negative gradient direction. That simple loop is the engine inside every single deep learning library.
But with every step comes a critical decision. How far do you jump? And this brings us to probably the most frustrating hyperparameter in all of machine learning, the step size, or as it's more commonly called, the learning rate.
Back to our blindfolded hiker. You know the direction of the steepest slope, but if you take a tiny shuffle, you'll take forever to get down the mountain.
But if you take a giant leap,
You could jump right over the bottom of the valley and land halfway up the other side, making your loss even worse.
and the sources had a great example of this. They started with a loss of about 2.2, with a really small step size, like 1e6. They made steady progress, getting the loss down to 1.6.
Yep, slow but steady. But when they increased that learning rate just 10 times to 1e5, the algorithm completely overshot. The loss exploded up to 2.8.
So that's tightrope. Too low, and you're too slow. Too high, and you diverge. Just bounce around or fly off into a bad region.
And this problem gets even harder when you think about the size of modern data sets. Millions of images. Calculating the gradient over the entire training set for every single update would take days. It's not practical.
Which is why we use a really clever workaround. We move from full gradient descent to mini-batch gradient descent.
Instead of calculating the true gradient, which is the average over all million examples, we approximate it. We just calculate the average over a small random subset, a mini-batch, maybe 256 examples.
That seems like a pretty wild approximation. Why does that even work?
Because there's so much redundancy in big data sets. I mean, the gradient you get from one batch of 256 CAD images is going to be very, very similar to the gradient from another batch of 256 CAD images. You get a good enough estimate of the downhill direction, but it's orders of magnitude faster.
And this is where the terminology can get a bit confusing. Technically, stochastic gradient descent, or SGD, means using a batch size of just one.
Right. But in practice, everyone uses the term SGD to refer to this mini-batch process. It's become the common name for it.
You also see these mini-batch sizes are always powers of 2, 32, 64, or 128. What's that about?
That's purely a hardware optimization. GPUs and other processors are just much more efficient at doing matrix math when the dimensions are powers of 2.
Okay, so mini-batch SGD is fast. But we said that with neural networks, we're not in a smooth bowl anymore. We're in that bumpy, non-convex terrain. What kinds of problems does that create for this simple gradient descent?
There are three huge problems that simple SGD runs into in these spaces.
Okay, what's the first?
Poor conditioning. Imagine you're in a long, narrow canyon. The walls are incredibly steep, but the floor of the canyon is almost flat.
I see. So the loss changes really fast if you move side to side, but very slowly if you move forward.
Exactly. And vanilla SGD will just jitter back and forth between the steep walls, making agonizingly slow progress down the flat valley floor.
The second problem is getting stuck.
Right. Local minima and saddle points.
Yeah.
You get to a spot where the gradient is 0, so you stop moving. Now, in high dimensions, it's actually rare to get stuck in a true local minimum. It's much more common to hit a saddle point.
Which is what, exactly?
It's a point that's a minimum in some directions, but a maximum in others, like the middle of a horse's saddle. The gradient is 0, but you're not at the bottom. Simple SGD gets paralyzed there.
And the third problem is one we actually created ourselves. Gradient noise.
Precisely. Because we're only using a mini batch, our estimate of the gradient is noisy. It's not the true direction. This makes our path down the hill really jittery and erratic.
So this combination of a harsh landscape and a noisy compass requires more advanced tools. This is why we have adaptive optimizers. Let's start with momentum.
Momentum adds inertia. Instead of just looking at the gradient from the current mini batch, it calculates a velocity as a running average of all the past gradients. There's a friction factor, usually called rho, Laurel, that's set high, like 0.9 or 0.99.
So it has a memory of where it's been going.
Exactly. And that inertia lets it smooth out the noise from the mini batches and gives it enough momentum to just roll right over shallow local minima or through saddle points. It stabilizes the whole process.
Okay, that helps with the noise and getting stuck. But what about the narrow canyon, the poor conditioning? For that, we need something like RMS prop.
Right. RMS prop tackles that problem by giving every single parameter its own adaptive learning rate. It keeps track of a running average of the squared gradients for each parameter.
What does that do?
It's simple, but really powerful. If a parameter has seen really big gradients in the past, that's the steep direction across the canyon. RMS prop shrinks its learning rate. If a parameter has seen tiny gradients, the flat direction down the canyon floor, it boosts its learning rate.
So it dampens the jitter and speeds up the useful progress.
It completely fixes the poor conditioning problem. And that brings us to the modern default, the champion optimizer, ADAM, which stands for Adaptive Moment Estimation.
And ADAM just combines the two ideas.
It takes the best of both. It tracks the first moment of the gradient, the running average, just like momentum, to handle noise and saddle points. And it tracks the second moment, the squared gradients, like RMS prop, to handle the poor conditioning. It's just a robust, all-in-one solution.
So for anyone starting out, the rule of thumb is just use ADAM.
Start with ADAM. Use the default parameters like a beta 11 of 0.9, beta 22 of 0.999, and a learning rate around 1E3 or 5E4. That's a great starting point. But even M benefits from not having a constant learning rate.
You're talking about learning rate schedules, lowering the rate over time.
Yeah. As you get closer to the bottom of the valley, you need to take smaller steps to settle in nicely. If you keep the same large step size, you'll just bounce around the minimum forever. So schedules like step decay or cosine decay let you slow down as you get close.
And sometimes you even need to start slow before you speed up, this linear warm-up thing.
Absolutely. Right at the beginning, when the weights are random, the gradients can be massive and unstable. A large learning rate can make the loss just explode. So you start the learning rate at 0 and slowly ramp it up over the first few thousand steps to let the model stabilize.
Okay, so to recap the journey, optimization is this brutal search for the bottom of a crazy high-dimensional landscape. Random guessing is useless.
Gradient descent gives us the path. But vanilla SGD is too simple for the harsh realities of this non-convex terrain.
So we add momentum to get past the bumps and noise and adaptive rates with RMS prop to navigate the narrow canyons, and then ADAM combines them into a powerful default tool.
ADAM is almost always a great choice, though sometimes a very carefully tuned SGD with momentum can just inch it out in performance. But we're talking about first-order methods here. They only look at the gradient, the slope.
Which leads to our final provocative thought for you. Mathematically, we know there are better ways to do this. We could use second-order optimization.
Second-order methods, like Newton's method, don't just look at the slope. They look at the curvature of the function. They use something called the Hessian matrix, which tells you how the slope itself is changing.
So that's like having a perfect topographical map of the terrain instead of just feeling the ground under your feet. It should tell you exactly how far to jump to land at the bottom.
It can. offering much faster convergence. So why don't we use it?
The cost of printing that map is just too high.
It's computationally intractable. If you have dollar parameters, the Hessian matrix has null squared elements. Inverting it to find the step takes null cubed time.
So for a model with millions of parameters,
It's impossible. The sheer cost forces us to stick with these efficient first-order methods like Adam. We trade mathematical perfection for speed.
and that leaves us with our next big question. We know we need to use the fast analytic gradient, but for the complex neural networks we're about to build, how on earth do we actually calculate that massive vector of derivatives efficiently?
And that is the puzzle that is solved by the single most important algorithm in all of deep learning, backpropagation.
That's where our next deep dive begins. Until then, keep exploring.